Welcome again. This is lecture 5 of EC253C. We have been discussing about 8085 microprocessor. In last class, we studied about the internal architecture of 8085 microprocessor. Let me briefly recap what we have studied so far. The internal architecture of 8085 microprocessor, or for that matter any processor, the essential items are we have a arithmetic and logic unit, that's okay. Then we have timing and control signals, which actually generates the necessary timing and necessary control signals to execute different instructions inside arithmetic logic unit. We have a register array here. There are different registers. Some have special functions, we call them special function registers, right? Like register A, register F, stack pointer SP, program counter PC, increment decrement register. Or there are also two more registers here: instruction register, instruction decoder. There might be many more registers inside 8085. We don't need to know every register. And these are and some are general purpose: B, C, D, E, H, L. And also there's an 8-bit data bus which internally connects these register arrays with ALU, or ALU with memory, or these registers. This 8-bit data bus, internal 8-bit data bus, has been shown in green here. So this 8-bit data bus may connect these registers with memory, or maybe these registers with ALU, or this ALU with memory. And then we also have a 16-bit address bus, A0 to A15 here in red, and this address bus is actually used to select any address from the memory. And a part of these, the lower part of this address bus, A0 to A7, is also used for data transmission between memory and processor. Processor may be registers, or directly to ALU. So we have named it AD0 to AD7 and A8 to A15. So I have explained broadly the flow of the program, the flow of information, or how a program actually gets executed, how are instructions executed inside a processor. I have not explained each of the registers in detail. I think I only explained this program counter. What's the job of program counter register? It's a 16-bit register, and it holds the instruction, or it holds the address of the next instruction that processor needs to execute. So naturally, by default, at the start of the program, when we power on our processor, it will have an address 0000, because it expects the first opcode, the first instruction, to be stored at 0000 memory location. And then after executing this instruction, it increments itself continuously unless and until we power off the system or we reach to the end of the program. That's it. So before discussing other registers like A register, F register, or stack pointer, I might want to discuss about one more model of 8085 microprocessor, or one more model of the processors. That's known as programming model. Actually, this is more important than discussing the detailed internal architecture of any processor, for two reasons. Reason number one: usually manufacturers, they don't publish the whole internal architecture of any processor, but what they publish is only the programming model of a processor. And reason two: the programming model is actually what a programmer needs so that he can program the system easily. It's actually the necessary thing that programmer needs to study before programming a particular processor. What exactly is a programming model? It's a simplified model showing only those things, only those registers, only those important parts of the processor that are actually important from the point of view of a programmer, in the sense that a programmer must need to know these things about the processor before he can write a program. He must know certain types of registers, he must know the connections between certain registers and maybe ALU, he must know some other things before he or she can write a program for this very particular processor. That model is known as programming model. So here we will be discussing the 8085 programming model. And number two thing, I have already told you that programming model is actually the model which companies, which manufacturers publish for the general public. Sometimes, most of the times, they don't publish all the internal details, the internal architecture of a processor, but what they publish is the programming model only. So programming model, studying about the programming model of a particular processor is therefore more important because of two reasons. One, it's a programming model that is actually available to the common public, and the second thing, programming model is necessary if one wants to program a particular processor. So what is given in the programming model? It's a simplified model of a processor. What is given inside, what is given in the programming model of 8085 processor? Programming model of 8085 processor simply shows us some registers which are important from the point of view of a programmer. The register arrays we have been discussing so far. Okay. And then we might have something known as data bus and address bus. This address bus, unidirectional, 16 lines. Then this is data bus, bidirectional, only 8 lines. And we have also studied that actually data bus is a part of address bus. That's okay. And then the registers here, we have already studied these registers. So the first we have accumulator. Or simply we sometimes call it only A. It's a very accumulator, or let me simply write A. And then we have another register, and this is flag register. It's also very important register. We have not studied about these registers yet. We have 6 general purpose registers: register B, C, D, E, H, L, and then stack pointer, I will call it SP, stack pointer, and program counter. This is all in the programming model of 8085. Programming model of 8085. This is everything. So we will be more concerned about knowing the exact function of these registers only. Register A, flag, B, C, D, H, L, stack pointer, and program counter. We already know what is program counter used for. Before studying other registers, let us take some time about discussing about various instructions that 8085 can actually execute, because those instructions, if we know those instructions, that will actually help us knowing the exact function of these registers. One more thing, most of the books, since the exact internal architecture is not published by most of the manufacturers. So most of the books you will find that in most of the books you will only find the programming model of a particular processor. In fact, the Gonker, the textbook for 8085 microprocessor, that only mentions the programming model of 8085 microprocessor. Similarly, for other processors, in books and in other literature, you will only find programming models, and this programming model is actually important for a programmer. So before getting back to these registers, let's take some time about discussing various operations that 8085 processor can actually execute inside its arithmetic logic unit. So various operations. First of all, what are these operations? These operations are actually primitives. These are actually primitives that are actually used to write any complex program. Any complex program will actually be constituted by these small operations like AND, like add, like subtraction, like move. And these operations are actually operations that a particular arithmetic logic unit of a particular processor is capable of executing. And these instructions, these operations, what a particular processor is actually capable of executing may vary from one processor to another processor. For some processors, there may be only few instructions that its arithmetic logic unit is capable of executing, but for other processors there might be few hundred instructions, few hundred operations that ALU is actually capable of executing. In case of 8085, I have already told you that the arithmetic logic unit inside 8085 processor is capable of executing 74 different instructions. I think the number is right, 74 different instructions. That translates to 256 different operations, but 74 unique operations. So we must know our processor, the arithmetic logic unit inside our processor 8085 is capable of executing only 74 different instructions, and these 74 instructions constitute the instruction set of our 8085 microprocessor. And we may write using these 74 unique instructions, using these 74 operations, using these 74 primitives, we may write any complex program. We'll come to that later in subsequent lectures, how we write programs using these basic operations. These 74 instructions have been divided into 5 different categories. 5 categories. Number 1 category is data transfer instructions, data transfer operations. Such instructions, and for each instruction we have a mnemonic, we have an opcode, we have a particular binary pattern. And data transfer operations are such operations that are actually used to transfer data from one location to another, maybe between registers, maybe between memory and registers. So I have given an example of data transfer operation, move. Move is a data transfer operation which actually transfers data, copies data from one location to another. The second category is arithmetic instructions. Arithmetic operations, instructions that pertain to arithmetic operations. And the easiest example here is add, an instruction that may add two 8-bit numbers, and we call it, the mnemonic here we have used is ADD, add. The third category of operations is logical operation. Those instructions which do logical operations. We may have examples or anything. These are those types of instructions which do logical operations on data. The fourth category here is branching operations. What are branching operations? If you remember, in the last class I told you, or in this class also, I told you that program counter will have a value of 0000 initially. I am writing in hex. From now on you should remember, whenever I write whenever I write a number, it is to be in hex unless I specify it otherwise. So 0000 is hex 16 zeros in binary. So at the start of the program, when we power on our processor, it will have a value 0000. So it will fetch the first opcode from memory location 0000, and then after executing that instruction, whatever opcode we have at 00000, it will increment itself to 0001, execute the next instruction at 000001, and then increment itself again, and the program will run sequentially. But sometimes we don't want program to run sequentially. We have to make certain decisions. You may have seen in your C programming course, like we make decisions like if this, then do this. So there might be decisions, there might be few instructions that are written here and few instructions that are written somewhere else, and depending upon some parameter, depending upon some value, in some cases we might, after instruction 2, we might want to execute these 3 instructions, but in some other case we might, after instruction 2, we might want to execute these 3 instructions written somewhere else. At that time we need these branching operations. And also sometimes, as you have seen in C also, we need to execute a group of instructions repeatedly, like in subroutines, like in functions. We have a block of instructions that constitute a function, and we might execute this group of instructions repeatedly. Also in loops, we have loops that run a particular group of instructions many times. So at those times we don't want our program counter to increment itself sequentially, but we want that some other value may be fed to this program counter. At that time we need branching operations, and they may be jumps or they may be calls to subroutines. We will see in future lectures. And then we have the last category of instructions, that actually known as machine control instructions. Machine control instructions or machine control operations. Those types of instructions which don't do actually any function, which don't manipulate the data, but they control the machine. Like one example is halt instruction. Halt, the name is halt. Sorry. H-A-L-T, halt. It's used to pause the program, pause the execution of the program. Or another instruction we might have NOP, no operations. It doesn't do anything. And why we need an instruction that actually does nothing, we may see that in future lectures. But for now, there are instructions that actually do nothing, like halt. It pauses the program, does nothing. NOP, no operation, it does nothing. It just wastes some of the CPU time, nothing else. So these are 5 types of operations that actually may be performed, that actually are performed by our 8085 processor. These are data transfer, arithmetic, logical operations, branching operations, machine control operations. And I have given examples of each category. I think next we should take some examples from each category and explain those instructions in much more detail. So let's move on. Let's start discussing these instructions one by one. Of course, we will not be discussing all 74 instructions, but we will be discussing some important ones. So let's start with these data transfer instructions. One thing you should remember during the discussion of these instructions, you should remember the programming model of 8085 microcontroller. Sorry. We have accumulator, we have flag register, then we have B, C, we have D, E, H, L, and then we have two more registers as program counter and stack pointer. Okay, so first instruction, it is MOV. Two important data transfer instructions I want to discuss is move, MOV, and MVI. These are both move instructions. This we say move, we read as move, and this we read as move immediate. What's the difference? We are going to discuss. The things you should remember about these instructions: each instruction has its associated binary pattern, 8-bit binary pattern, that actually gets written in the memory. These are only mnemonics, codes which have been attributed to those bit patterns so that to make life of a programmer easier. Okay, so what's the general syntax of, first let us discuss this instruction move immediate. What's the general syntax of this instruction and what it does? Move immediate, it says its general in syntax is something like this: MOV move immediate. And then one more thing you have to remember: with each instruction there are two parts. The first part is known as opcode, which actually tells what to do: move immediate, move something. Then the second part is operand part, why to find the operands, why to find the data on which to operate. So move immediate, as the name suggests, it has to move some data. So we must give it some source and some destination, where from to move, and from where to copy, and then where to place it. So the general syntax here will be in move immediate case: move immediate R, comma, any 8-bit number. What is this R? This R is any 8-bit register. Maybe A, maybe B, maybe C, D, E, H, L. So this R here represents any of these registers, accumulator and any general purpose register B, C, D, E, H, L. And this 8-bit number can be any number, any 8-bit number, any number from 0 up to 255. For example, if I want to store some data in accumulator, maybe I want to store number 23 in accumulator, so I will write something like this: move immediate accumulator A, represent, and then this data 23. Or if I want to save some other data, maybe in register B. I can simply write move immediate B, some other data, maybe 12. Okay, fine. This number here is in decimal, but actually the general practice is to write this number in hex. For example, the hex of 23, or maybe I will change 23 in binary. It will be 0111 and 0001 to give it a 8-bit shape. 1 2 4 8 16 20, it's 23. Okay, similarly I can write 12 as 0000 1100. This is 23 and this is 12. Or in hex I can write 23 as this is 1 1 2 4 1 7, and this number is 12 in hex is 0 1 2 12. 12 is 10 11 12 ABC 0C. So I can write something like this: move accumulator. And now this 23 I have to write in hex. I may write in decimal also, that's also fine, but the common practice, because everything here is in binary, so we write in hex actually, and hex and binary are easy to interconvert. So 23 will be 17, so I will write 17. But just to let the compiler know that it's in hex, I will write a simple H here. Move accumulator 17H. So what will this instruction do? When this instruction is copied inside the instruction register, it is decoded, it will be executed. What will actually happen? Our ALU will actually copy this data 17 hexa, 17 in hex, that is 0001 0111, and put it in register A. Simply if I write move immediate B and 12 in hex is 0C 0CH, what will happen when this instruction is executed? A particular bit pattern, that is 0000 1100, will be copied in register B here, okay, inside the processor. Then we have move. Again we will be studying first about the general syntax. What was the general syntax of move immediate? It was MVI, any register we represent by R, and then any 8-bit number. 8-bit numbers can be from 0 to 255, or in binary they can be from 0000 0000 up to 1111. It's one more 0 1111, or in hex 0 to FF. Similarly, the general syntax of move instruction, simply move, not immediate. It has the opcode is move, but it will, here we have two operands. Here also we had two operands. One was immediate operand. The operand word itself present in the instruction. That's why it's called as move immediate. But here it's there's something different. We have two registers, RD, RS, and these RD and RS, they are also known as source register and destination register. And again, RD and RS both can be any general purpose register, B, C, D, E, or can also be H, L, and all can also be accumulator A. Accumulator is a special function register. In some time you will be knowing why what is the exact function of accumulator in 8085 microprocessor. So for example, I can write here MOV move mov move rd any register. I can write a comma any other register b. So when this instruction will be executed inside the processor, what will happen? Whatever is in b will be actually copied to a. Of course, the contents whatever were in b will remain there, but a copy of them will be transferred to a. And what is in b? We don't know what is in b. Maybe we have written something in b prior to, before executing this instruction. If we not written anything, there will be all zeros, because by default in 8085 registers, when we power on 8085 register, when we power on 8085 processor, every register has a 0. So if the first statement in our program is something like this, move a comma b whatever is in b, and in this case, because this is the first instruction, there are all zeros in b, all zeros will be copied in a. In fact, in a there, already in a there were zeros. Maybe I can write something like this. I can write the first instruction is MVI B 23H 23 hex. Then I will write move accumulator B. So if I write this program, if I burn this program in my 8085 microprocessor, what will happen when the first instruction will be executed? So this is my programming model. This is accumulator, these are flags, these are all 8-bit registers. This is B, this is C, then I have D, E, H, L, then I have stack pointer and program counter. Okay, so 23 hex, the hexadecimal number 23 will be copied here, and when the second instruction will be executed, whatever is in B, that will be copied to A. So after the execution of second instruction, we have a number 23 hex in B, and also in accumulator 23 will be here. Maybe after that we have another instruction, move C A. What now? When this instruction will be executed, whatever is in A will get transferred to C. So we will have 23 here. Okay, I think this is very easy. What are these instructions? How exactly we use this instruction? It might be that you will not get that at this point, but in a couple of lectures you will get familiar with these instructions, and then you will be able to comprehend actually how these instructions are used to write any complex programs. There are other data transfer instructions also. We will not be going to study about those instructions yet. First, we will move to discuss some of the arithmetic instructions. Arithmetic instruction. Simplest of arithmetic instruction is add. Add is again the opcode, and where to find for add? You must remember, for any addition there should be two operands, there should be two numbers, and in case of 8085 there should be two 8-bit numbers that actually will be added to each other. So there must be two operands that this add operation will actually operate on, and then there must be a third location where the result will get stored. The general syntax of add for 8085 is something like this: add R, where again this R is only general purpose register B, C, D, E, H, L including A, accumulator. So by the looks of it, it seems that we are actually providing only one instruction, one operand that is stored in any register to our add instruction, where from it will get the second operand and where it will store the data. In 8085 by default, and we cannot change it, the second operand always comes from accumulator. the second operand in case of addition or also in case of other arithmetic operations comes from accumulator. That is, one of the two operands always comes from accumulator. The second is supplied by the instruction in the instruction using only general purpose registers, and these general purpose registers can be A also. And the result, where is the result stored? The result is always stored in accumulator. And what will this add do now? This add will actually add the contents of this register R to the contents of accumulator, and then will store the result in accumulator. For example, if I had some program like this, I had first three instructions exactly like this: move immediate B23H. I am actually copying a number 23H in register B. Then I am copying the contents of B to accumulator, and then I am actually copying the contents of accumulator to register C. After that, maybe I have the fourth instruction like something like this: add, or before that wait a second please. So we have let's take this example only. We have move immediate B23H. We have executed these instructions and we have these contents in our registers. The fourth instruction may be something like this: add, or before add we have another instruction: move immediate D5H. So we are actually moving 5 here, 5 in hex again. All the numbers are in hex. And after that we have another instruction and we are saying add, and we have to give it some instruction: add D. So what will happen when this instruction will be executed? We have executed the first instruction. We know what will happen. 23 hex will be copied to register B, and then in the second instruction the contents of register B will be copied to register A. Of course register B will retain its contents, and in the third instruction the contents of accumulator register accumulator will be copied to register C. Okay, and then in the fourth instruction some immediate data number 5H will be copied to register D. That's okay. Now in the fourth instruction, in the add instruction, what will happen? What does this instruction say? This instruction says add D. Add D to what? By default D is added to the contents of accumulator. That means whatever is in D, 5H means 0 0 0 and 0 0 1 0 1. This is 5H will be added to the contents of accumulator. And what are the contents of accumulator? 23. So we have 1 here, 1 1 0 0 0 1 0 1 1 1. This is accumulator. So contents of register D will be added to the contents of accumulator, and the result will be stored in accumulator. So when we add this we will get 1 1 1 0. That means 0 will be here, 1 is carry, again 1 1 10. So not 10 1 0 actually 2. So 0 is here, 1 carry, 1 1 1 1 1 3. So 1 is here, 1 will be here, 1 will be here, 0 0 0. So this number is 1. Sorry, 23 was in hex. I think I did it wrong. I will do it again. the contents of D will be added to the contents of accumulator. Contents of D are 5, that means 0 0 0 0 0 1 0 1, and then 23 is in hex. 23 in hex means 0 0 1 0 0 0 1 1. If you have any confusions here how 23 is in 0, I suggest you to go through the number system once again, maybe for half an hour or an hour. This is very easy. So this 23 and this is 5, so the addition will be 1 1 1 0, 1 here, carry 1 1 1 0, 1 again here, 1 1 1 0, then 1 0 1 0 0. So we have maybe 2 8x. So what will happen? This 28 will be stored in accumulator, overwriting the original, replacing the number what was there. 23 will be replaced by 28. So this is our program. This is how add operation works in 8085. We say add and name some register. The contents of that register actually get added to the contents of accumulator, and the result is stored in accumulator. I think that's okay for now. We will discuss some more instructions in next class. Thank you.